Hello everyone. This is the 8th week class. Today we are going to study a technique called factor analysis. Okay. Basically, there are two types of factor analysis. One is called exploratory factor analysis, and the other one is called confirmatory factor analysis. Today we are going to focus on exploratory factor analysis, and next time we are going to study confirmatory factor analysis, right? Exploratory factor analysis is used to explore the underlying structure of a set of observed variables. So in this case, we don't have any idea about the underlying structure of a data, right? And on the other hand, the confirmatory factor analysis is used to verify a factor structure that has already been defined. That means in this case, we know the exact structure of the data, right? And we want to verify that. Right? In that case, we use confirmatory factor analysis. Okay. We use software SPSS for exploratory factor analysis. On the other hand, we need to use AMOS for confirmatory factor analysis, right? Now let's talk about exploratory factor analysis. So what is it? Well, this one is used to group variables that are correlated and form factors, right? So grouping variables means a factor is a linear combination of the the observed variables, right? So as I said, this one is used when we don't have any idea about the underlying structure of the data, right? And the most critical reason to use this exploratory factor analysis is to remove some variables that are not grouped together. I mean, think about the case where we do the empirical study. So, for example, you create several questions for measure a specific thing, and then you do the exploratory factor analysis, and then you want to find which question is not grouped together to measure a specific thing, right? If you find one, then you need to remove that question for the your empirical study, right? So, for example, if you create 5 questions to measure, let's say, happiness, right? So you want to measure happiness, so you create 5 questions to measure happiness, right? And you do the exploratory factor analysis, and suppose it turns out that question 3 is not grouped together, then you need to remove this question, right, for your analysis, right? And as I said, SPSS is used for exploratory factor analysis, and if you want to do the confirmatory factor analysis, you need to use AMOS, okay? We'll talk about this when we study confirmatory factor analysis, right? And also the exploratory factor analysis is used to measure reliability, right? Reliability is a measure of internal consistency, right? Basically, you want to measure how closely related a set of items are as group. So to check reliability, you use a measure called Cronbus alpha, right? And if this one is greater than zero point 0.7, you can say that your data are reliable, right? Now let's look at the how to get the Cronbus alpha, right? Cronbus alpha is computed by using this thing, but it's very hard to understand this thing, right? So let me explain. Another one is called average split half reliability. Actually, this one is exactly same as Cronbus alpha when we have even number of variables, right? So let's try to understand this one and then try to understand Cronbus alpha, right? Basically, reliability checks how closely related a set of items are, right? So we need to compute correlations among the variables, right? Now, suppose that we have four variables, right? A, B, C, D. And we can think of three possible splits, right? So we can think of, this case is, right? And then you compute correlation between the splits, right? So you want to compute correlations, right, between these two, right? And then once you get the correlation, and then you take the average, right? That's the average split half reliability, right? Basically, this one is the average correlation, right? So Cronbus alpha is kind of average correlation, right? Now, when you compute the correlation between the splits, this one and this one, since this one contains two variables, right? You have to reduce this one to one, right? So in order to reduce to one, you need to take the average of these two, right? And also you need to take the average of these two, and then you can compute the correlation, right? Now let's try to understand the principles of factor analysis, right? So suppose we have data like this. We have five students, and then we have exam scores for each of three subjects, right? So finance, marketing, and HRM. HRM is what? Human resource management, right? Now suppose that the score for each course is a function of two factors. One is verbal and the other one is quantitative, right? So you can write the scores in terms of these factors, right? So y1 is y1 is finance, right? And y1 is a function of two factors, and y2 is marketing, right? Also, marketing is a function of two factors. And the last one, the HRM, is also a function of two factors, right? Okay. In this case, these coefficients, these ones are called factor loadings, right? If you look at these equations, factor loadings actually are the coefficients which represents the relationship between the factor and the original variable, right? Now try to understand the factor loadings, I mean the coefficients, It is reasonable to think that the verbal ability is related to marketing and HRM scores, right? And on the other hand, quantitative ability is related to finance scores, right? So we can say that scores for marketing and HRM are expected to be positively related to verbal ability. And the score for finance is expected to be positively related to quantitative ability, right? So I summarize the relationship in this table, right? These are the factor loadings. And for finance, we have positive relationship, right? Here. And for marketing and HRM, we have a positive relationship here, right? Since this factor 1 is the verbal ability and the factor 2 is quantitative ability, right? Now, so how to estimate the factor loadings? If you look at the equations that we wrote before, uh, we may think that we can use regression, right? But in this case, we cannot use a regression because factors are not observable, right? So we have to use different method for estimating the factor loadings, right? In order to do that, we need to make some assumptions. So assumptions for errors and assumptions for the factors, right? So in this case, the expected value of error is equal to 0, and the variance of error is a sigma square, right? And the expected value of a factor is equal to 0, and variance of a factor is equal to 1. This is because in this case, we are assuming that factors are standardized, right? If you standardize, the mean is equal to 0 and the variance is equal to 1, right? So the variance of each variable turns out to be this, right? And in this case, the this one is called communality, right? And basically, the communality is a variance explained by factors, right? And in this case, sigma square is a variance unexplained by factors, right? If factors explain the scores perfectly, then sigma square is equal to 0, right? And covariance between the variables, right, turns out to be this, right? By using the the assumptions, right? By using this, we create a theoretically computed variance and covariance table like this. Okay. And if we use the actual scores for 3 subjects, we can compute the variance and covariance like this, right? So the basic idea is that we want to estimate loadings, right, in a way that variance and covariance computed theoretically are as close as possible to the variance and covariance computed from the actual observations, right? So let me explain this one again. So we want to estimate loadings, right? Factor loadings in a way that this one is as close as possible to this one, right? Before we go further, we need to know this fact. There can be many combinations of factor loadings that can generate the same variances and covariances, right? So I'm showing you the example here. We have two sets of factor loadings, and these ones generate the same variances and covariances like this, right? That means we should not stop simply when we find a set of factor loadings, right? Instead, we should try to find a better set of factor loadings, right? So this process is called factor rotation, right? So how do we find the factor loadings? We usually use a method called the principal component. Remember that we want to find factor loadings, right, which makes the theoretical variance covariance table as close as possible to the variance covariances computed by using the actual observations, right? In case of a principal component, we only look at the variances, not the covariances. So in principal component method, right, we only consider the variances, right? And this one is from the actual observations, right? And you wanna find the factor loadings, right? Here, these are the variances, right? For the theoretical variance covariance table, right? So you wanna estimate factor loadings, right? To make T1, right, be as close as possible to T0, right? As a matter of fact, in SPSS, the principal component analysis is used as a default. And also in this case, the observations are standardized, right? That means what? The variance of each variable is equal to 1, right? Now let me show you how to get the computer output, and then let's try to understand the outputs, right? Now let me show you how to do the factor analysis. So this is exploratory factor analysis, right? So I already put the scores for finance and marketing and HRM, right? So once you put your data, you go to the analysis, right? In this case, you choose, this is dimensional reduction, right? And you take the factor analysis, right? And you move your variables to the right. And you go to the, this is factor rotation, right? You usually go to here and you choose Verimax. Usually you do the Verimax, right? And continue and enter. So you get the results here, right? And you get two things here, before rotation and after rotation, right? So you get the these results. So I'll show you how to interpret, these results, right? Now let's do another example here. Now let me use new data. Here I have five variables, right? So if you want to do the exploratory effect analysis, you go to the analysis and you go to dimensional reduction and you go to the effect analysis, right? And I already moved five variables to the right? And you go to the effector rotation, you choose a Verimax and continue and enter, right? And you get the results like this, right? So in this case, we have two factors here, right? 1 and 2. I'll explain why we have two factors, right? Very soon. Actually, you look at the eigenvalues and you select factors which has a greater than 1 in terms of eigenvalue, right? So in this case, 1 and 2 are selected, right? Now this is before the rotation and this one is after rotation, right? These are the factor loadings, right? These numbers. I'll explain how to interpret these things, right? Now, let me show you how to get the Cronbus alpha, right? So if you want to get the Cronbus alpha, right? So you need to know which variables are grouped together, right? So once you do the factor analysis, right? You see that in this case, variable 2 and 3 are grouped together, right? I'll explain this, why these are grouped together. Now suppose that, 2 and 3 are grouped together, right? Then you need to check the reliability check, right? So you go to the analysis, and in this case, scale analysis, right? And this is reliability, okay? And you move the variables that are grouped together, right, to the right, and you click this one, and then you get the Cronbus alpha value, right, here. So let me show you this one again. So in this case, if you do the factor analysis, so in this case, if you look at the results, so I'm looking at the rotated, right, factors. In this case, x1 and x3 and x5 are grouped together. And in this case, x2 and x4 are grouped together, right? 1, 3, 5. Once you find that, and you go to the analysis and go to the reliability, right? And move 1, 3, and 5 to the right, and You click this one, and you get the Columbus alpha 0.823, right? Right? This is how you get the Columbus alpha, right? Now let's go back to PowerPoints. So we are back to PowerPoints. This is the output for factor analysis, right? So we had three variables: finance, marketing, and the HRM scores, right? And it turns out that we have two factors here, 1 and 2, right? I'll explain why we have two factors here, right? And these ones are factor loadings, and these ones are called eigenvalues, right? I'll explain this very soon. And these ones are the percentage of variance explained by factors, right? So let's try to understand this output, right? So first thing, factor 1 explains 66% of the total variance, and the factor 2 explains 33% of the total variance, right? Here, these are the percentage of variance explained by factors, right? And the second one, factor 1 seems to be verbal ability since we see high factor loadings for the variable 2 and 3. Factor 2 seems to be quantitative ability since we see high factor loading for the variable 1. If we look at the factor loadings, right, here, so we have a high factor loading here and a high here, right? These ones are low, right? Since we have high loadings for variable y2 and y3, right? So this factor is called verbal, right? And second factor is quantitative since we have a high factor loading for y1, right? Here. And sum of factor loading squares for factor 1 is 1.981, and the sum of factor loading squares for factor 2 is 1.008. Sum of factor loading squares for factor 3 is 0.01. Let me explain this one. So how you get the 1.981? So you square these things, right? You square these things and you add, right? So you get 1.981, right? And then you square these things and you add, so you get 1.008, right? So this is the eigenvalue, right? Now, factor 1 and factor 2 are selected if the criterion in this case is initial eigenvalue is greater than 1 is used, right? The reason that factor 1 and factor 2 are selected is that their eigenvalue is greater than 1. If we look at the output, right, this one and this one is greater than 1, right? So we have two factors are selected, right? So let me explain the eigenvalue, right? Eigenvalue is the amount of variance accounted for by a factor, right? The reason that we apply the rule of eigenvalue is greater than 1 for selecting factor is the following. Data are standardized before doing a factor analysis. Right? Standardizing means what? We use z, right? So you transform x to z by using the, this one. So variance, as you know, variance of z is equal to 1, right? Thus, variance accounted for by a factor should be greater than 1, since a factor should be better than a single variable, right? Factor is a combination of original variables, right? So factor should be better than a single variable. So that's why the eigenvalue should be greater than 1 if factors are selected. Now the computer output can be rewritten as follows, right? These are the variances for the variables, right? The reason that these numbers are 1 is that variables are standardized, right? So variance of y1 is equal to 1 and y2 also is equal to 1, y3 also is equal to 1, right? That's why we have 1 here, right? And these are the loadings, right? Factor loadings. And for the first factor and the second factor. And remember that this number comes from you square these things and then you add, right? And also this one comes from you square these things and then you add, right? And if you square these things, right, and you add, you get these numbers, right? Right? And remember that we want to find factor loadings, which makes, right, this one is be as close as possible to this, right? So in this case, almost, same, right? Now let's talk about the factor rotation, right? If you have clear differentiation among factors, right, in terms of factor loadings, you don't need to do the factor rotation, right? Difference among factors is not clear, right? Then you need to do the factor rotation, right, to get better ones, right? In that case, you usually use either Verimax or Quartimax, right? The difference between these two comes from this, right? Verimax maximize the variance of squares of loadings for each factor, and Quartimax maximize the variance of squares of loadings for each variable, right? You usually do the Verimax, right? When you do the factor analysis. If you don't get good results, even if you do the Verimax, then you try to use another one, right? For example, Quartimax, right? So let's look at the output again here. So this is the factor loadings before, rotation, right? In this case, it's very clear, right? Clear means that the difference between factors is very clear, right? For factor 1, we have a high loadings here, right? For variable 2 and 3. And for factor 2, we have a high loadings for variable 1, right? These ones are very low, right? Okay? So in this case, it's very clear. So you don't need to do the factor rotation, right? And as I said, these ones are eigenvalues, right? So you select the factors which has eigenvalue of greater than 1, right? So in this case, factor 1, factor 2 are selected since these numbers are greater than 1, right? Next time, we are going to look at the confirmatory factor analysis, right? let's stop here. See you next time.